Dear students, last class we are discussing about the theory of grating. Right? We arrived two conclusions. One is, in order to have bright band by using grating, condition required is E plus D sin theta is equal to n lambda. Here n is an integer, takes values 0, 1, 2, 3, so on. Lambda is the wavelength, theta angle of diffraction, and E plus D is termed as grating element. Similarly, for dark fringe, condition required is capital N into E plus D sin theta is equal to m lambda, where m takes values 0, capital N, 2n, so on. Now, here m takes, what is capital N? Number of slits in the grating. In order to have high intensity diffraction lines, number of lines should be very large in grating. Now, in practical grating or the grating used in our laboratory, generally it consists of 15,000 lines per inch. Consists of 15,000 lines per inch. That means in 2.54 centimeters there are 15,000 lines. That means in 1 centimeter there are nearly 5906 lines. That's why here that capital here let it be n dash. Now grating element E plus D is equal to 1 by n dash, because here E is the thickness of the line and D is the distance of separation between the lines. Suppose diffraction pattern is formed like this, then E means thickness of this line, this thickness. D means this is E, and D is the distance between successive lines. E plus D is termed as grating element. In a grating, a very large number of lines arranged in a very small region. Now, here first one is how to determine the wavelength of spectral lines using grating. This can be done by using an instrument, that is spectrometer. Last class we have discussed something about spectrometer. Here main parts in spectrometer are, first one is collimator. First one is collimator. Here collimator consists of horizontal tube followed by slit at a variable slit. That means the width of the slit can be adjusted. That means the width of the slit can be adjusted. You can increase the width of the slit or decrease the width of the slit. And again, another end, second end of collimator consists of a convex lens, and this arrangement is placed in a vertical stand like this. Here, by adjusting the lens, it is made such that by using a rock and pinion screw, the slit is at the principal focus of the convex lens. Then what happens is, this convex lens emerges parallel light beam. Parallel light beam. If the width of the slit is extremely small, then it emits fine parallel beam. That means beam in which lines are parallel to one another and at the same time they are very sharp. When the width of the slit is very small. That's why in order to produce parallel light beam using collimator, the width of the slit should be extremely small and the slit is at the principal focus of the convex lens. Next, second one is that is prism table or grating table. The table which is used to place the grating. Let it be the position of grating. Here it consists of a circular scale like this. By using this circular scale, we can determine the angle current. Angle current by the system or grating can be measured by using the circular scale. Again, it is followed by telescope. Here, the telescope consists of again a convex lens here, and again it consists of an eyepiece here. Here, we are using Ramsden's eyepiece in this telescope, because by using Ramsden's eyepiece, we can make measurements. Right? Initially, it is adjusted such that that is the source of light, incident or travels to the slit and incident on the convex lens containing the collimator. Then the collimator produces parallel light beam, and the collimator produces parallel light beam. And again, this parallel light beam comes into picture of this telescope, and we can observe this parallel light beam or central slit, narrow slit, by using the telescope. It is adjusted such that the slit, image of the slit coincides with horizontal cross lines in the telescope. Again, next, first adjustment is the telescope is turned through an angle 90 degrees. Then this is the position of telescope. Here. Now, the grating is placed on the table and it is rotated through an angle 45 degrees. Then what happens is, for the same incident wave, if the mirror or lens turns through an angle theta, the reflected ray turns through an angle 2 theta, then it makes 45 degrees to the horizontal, and this grating makes 45 degrees with the horizontal. Then the reflected ray again coincides with the midpoint of cross lines in the telescope. Then the circular table is rotated through another 45 degrees and is made perpendicular to the parallel light beam coming from the collimator. Then it is said to be in normal incidence position. This is an experimental purpose one, and it can be demonstrated and observed by using the experiment. Okay, later we will discuss this experiment in a detailed way in our syllabus course. Now, now we can observe on the grating. Here it is the position of source, and here it is the position of grating here. And suppose let it be the screen here. Then on the screen we can observe different pattern like this. This actually this is not straight line. Take this here. Let it be the first order spectrum R1 here. Here also again first order spectrum. Again second order spectrum. Again third order spectrum. By using grating, we can find different order spectra. This first order spectrum, suppose we are using white light as source of light. The first order spectrum contains different colored lights, different colored light. And again, suppose we are adjusted the telescope such that the yellow line belongs to R1, coincides with the intersecting point of cross lines, its reading is noted. And again, the straight reading is again noted. Difference between these two gives you the diffraction angle theta. Similarly, same line can be observed in the other side also. And again, by taking reading on the other side and central reading, we can find the value of theta. Or we can find the yellow line reading on either side, and difference of those two gives you the value of 2 theta. Here, theta is the angle of diffraction. Once you know the value of angle of diffraction, condition for grating is E plus D into sin theta is equal to n lambda. Here, theta is the angle of diffraction that can be measured by using this instrument or spectrometer. Here, n is the order. First order means for a first order n is equal to 1. E plus D is the grating element. E plus D means E plus D is equal to 1 by n dash, where n dash is the number of lines per centimeter. N dash is the number of lines per centimeter. By substituting all these values, we can determine the wavelength of spectral line. That means similarly, yellow color line or red line or blue line, whatever it may be, in first order, we can determine the wavelength of different colored lines. Similarly, we can determine the wavelengths of different colored lines in second order and third order also. That is the experiment of determination of wavelength of spectral lines using grating, using diffraction grating. Now, here another important aspect is resolving power of telescope. What is meant by resolving power? Resolving power of any instrument is the ability. Resolving power of any instrument is the ability to show the two lines distinctly. How far it shows distinctly the two lines. That is the ability of that instrument. Now we are discussing about the resolving power of the grating. Here, in the case of resolving power of grating, basic principle is Basically, we know that in the case of single slit, suppose theta or alpha is taken on x-axis, theta or alpha is taken on x-axis and intensity on y-axis, we get a graph like this. This is the case in case of single slit diffraction. Here this is principal maximum. This is principal maximum. In order to observe the two lines strictly by using a grating, in order to observe the two lines strictly by using a grating, this is the principal maximum of for one line having wavelength lambda, at this angle of diffraction with theta. In order to have another line, here also for second line's principal maxima should be like this. That is, the secondary maximum of first one became the primary maximum of second line. For second line, let this angle be theta plus d theta and wavelength be lambda plus d lambda. Now, from grating equation, we know that condition for bright band is, grating equation is E plus D into sin theta is equal to n lambda. That is for one line. For successive line, E plus D sin theta plus d theta is equal to n into lambda plus d lambda. Next, in order to have the dark fringe or in order to have dark line, condition required is n into E plus D is into sin theta, n into E plus D into sin theta is equal to m lambda, where m takes values 0, capital N, 2n, so on. Here n takes values 0, 1, 2, 3, so on. Here the secondary maximum of first one should be the primary maximum of second line. In order to satisfy that condition, n into E plus D into sin theta plus d theta, sin theta plus d theta is equal to n plus 1 into lambda. n plus 1 into lambda. Here m takes values 0, n, 2n, so on. This is m is equal to nn. That means when m is equal to 0, nn is equal to 0. When m is equal to capital N and m is equal to small 1, it becomes n. Again 2n and so on. Here this plus 1 indicates the secondary maximum of first one should be the primary maximum or central maximum of second line. That is, here let it be the position of central maximum of first line having wavelength lambda. Here it is the secondary maximum. It should become the primary maximum of second line having wavelength lambda plus d lambda. Now, suppose we are multiplying this equation by capital N. Then what happens? Capital N into E plus D into sin theta plus d theta is equal to n lambda plus d lambda. n lambda plus d lambda. By comparing these two equations, one is n lambda plus lambda is equal to n lambda plus n d lambda. From this equation, lambda by d lambda is equal to nn. Here, lambda by d lambda is termed as the resolving power of grating. Lambda by d lambda is termed as the resolving power of grating. What is lambda? Here, for one line, wavelength be lambda 1 and for another line, wavelength be lambda 2. Then lambda is the average of lambda 1 and lambda 2. That means lambda is equal to lambda 1 plus lambda 2 by 2. What is d lambda? D lambda is the difference of wavelength between lambda 1 and lambda 2. In this way, here resolving power of telescope depends on what? The resolving power of grating depends on what factors? One is small n and another one is capital N. One small n means order of diffraction. First order, second order or third order, whatever it may be. Small n is the order of diffraction and capital N is the number of slits in the grating. Number of slits in 1 centimeter in the grating or total number of slits in the grating. As the total number of slits increases, As total number of slits increases, resolving power of grating increases. As the order increases, again also grating the resolving power increases. In this way, we can determine the resolving power of telescope, and again by using grating, we can make 3 experiments in this course or in this semester. One is grating normal incidence. Grating normal incidence. By placing grating in normal incidence position, we can measure the wavelength of spectral lines. Second one is resolving power of grating. Third one is grating minimum deviation. All these experiments can be carried out by using grating along with spectrometer. Whatever may be the case, while using a spectrometer, we should make some fundamental arrangements. First one is, it should receive, or the telescope in the spectrometer should receive the parallel light beam. In order to receive the parallel light beam, first of all, the telescope is focused to a distant object. By using rack and pinion screw, we can make such that the telescope receives the parallel light beam. Then we can find the fine image of the distant object. That is first assumption. Second one is, slit of the collimator should be as small as possible. When the slit belongs to collimator is extremely small, then the lines are fine. Lines are fine means they are having very low thickness and high intensity. And again, in order to produce parallel light beam by using collimator, the slit should be placed at the principal focus of the lens. And again, first of all, while making the experiment, in theory it is not necessary, but in the case of experiment, while making the experiment, first of all, we should measure the least count of circular scale. That is placed here. First of all, by determining the least count of circular scale, then we can find the reading at any position. Once you are able to find the value of angle of diffraction by using grating equation E plus D into sin theta, we can determine the wavelength of spectral lines. Once you are able to determine the wavelength of two lines lambda 1 and lambda 2, you are able to determine the wavelength of two lines lambda 1 and lambda 2, then you can find the average lambda is equal to lambda 1 plus lambda by 2 and d lambda is equal to lambda 1 difference lambda 2. By making this calculation, we can measure the resolving power. Here, by using a grating, the spectra are very fine and sharp. Strictly, we can observe two yellow lines which are very close to each other. By how far they are very close to each other, by adjusting the width of slit, when they becomes merged, again by taking the reading by using a special screw gauge, we can determine the grating in minimum deviation position, and again we can determine the wavelength of spectral lines, resolving power of gratings, and again wavelength of spectral lines in normal incidence position, resolving power of grating, and again grating should be in minimum deviation position. Such again that by using minimum deviation position also we can measure the spectral lines. The minimum deviation position is same as in the case of that is prism minimum deviation. You know the value of the prism refractive index mu is equal to sin a plus b by 2, sin a plus b by 2 by sin a by 2, where b is the angle of minimum deviation. That is the angle measured in minimum deviation position in the case of prism. Same can be done in the case of grating also. Okay, next class we will discuss the remaining aspects. So far we are discussing something about NZ, resultant of n sinusoidal disturbances, and again resultant of n sinusoidal disturbances. Next one is single slit diffraction, next grating theory, next grating normal incidence, and again grating resolving power. All these comes under Fraunhofer diffraction. In the next few classes, we will discuss something about Fresnel's diffraction. Okay, thank you.